Okay, so now that we've had our refresher on derivatives in Calc 1, let's ask ourselves, how could we go about taking a derivative of a scalar field? Remember, in Calc 1, you're typically just studying functions that have only one input, but in multivariable calculus, one studies scalar fields which have multiple inputs. So let's just start with an example here, and let's ask a question. So here I'm studying a scalar field, capital T, and the formula for capital T, so this is a scalar field on R2. Capital T takes two inputs, x and y, and the output here is giving me temperature, and it's y cubed plus x squared minus 2 times xy. So here I have a visualization of R2, that's the xy plane, and I have a sample point here with coordinates 3, 1. So one thing I could do with this scalar field is I could plug in the coordinates 3, 1, and the output here equals 4 degrees Celsius. So the idea is that at this particular location, temperature is 4 degrees Celsius. So if I was standing at the point 3, 1, I would observe a temperature of 4 degrees Celsius. So here's a question. Let's say that we were standing at this point 3, 1, and we wanted to travel maybe due east, or we wanted to travel due north. The question is, well, what would the rate of change of temperature be in either of those two directions? So if I wanted to travel due east, the question is, well, what would be the rate of change of temperature? And if I wanted to travel north, the question is, what would the rate of change of temperature be? So this is the question that the concept of a partial derivative answers. So if we think about this, we want to travel in one of those two directions. Perhaps we could use vectors pointing in those directions to define derivatives in those particular two directions. So this gives us the definition of a partial derivative of a scalar field. So the partial derivative of a scalar field with respect to the ith input variable is notationally defined as curly df divided by curly d x sub I. And just like in single variable calculus, the definition involves taking a limit of difference quotients. This is the limit as h approaches 0 of f of the input vector x plus h times e sub I minus f of the input vector x, all divided by h. So the idea here is that I'm taking my input vector x, and I'm adding this scalar multiple h of e sub I. And remember, our notation e sub I is referring to the ith column of the n by n identity matrix. So this is the definition of a partial derivative of a scalar field on n variables with respect to the ith input variable. Now, we're using the notation curly df over curly dxi. It is also quite common to see subscript notation. So instead of writing curly df over curly dxi, you'll also see people write f sub xi here. So both of those notations are very common. And while it might look intimidating to take, this limit definition might look a bit intimidating, it's actually quite easy to take partial derivatives. If you know how to take derivatives in Calc 1, you can take derivatives in multivariable calculus. The idea is that to calculate the partial derivative of f with respect to the ith input variable, we treat all of the variables not equal to the ith input variable as constants, and then we differentiate the expression with respect to the variable of interest. So hold everything constant except whatever variable you're studying, and then take a derivative with respect to that variable. So let's see some examples. Here's a scalar field on R2, and the formula is f of x1 comma x2 equals x1 squared plus x2 squared. So this is a very simple scalar field on R2. How would we take the partial derivative of f with respect to the first input variable? Well, in this case, we would hold the second variable constant, that's x sub 2, and then we take a derivative with respect to x1. So I do this by going term by term and taking derivatives. My first term is x1 squared. Well, the derivative of x1 squared with respect to x1 is, by the power rule, 2 times x1. Then I move to my second term here. My second term is x2, which I'm viewing as x2 squared, and I'm viewing x2 as a constant. So the derivative of x2 squared with respect to x1 is equal to 0. So partial derivative of this scalar field with respect to the first input variable is 2x1. But then I could take a partial derivative of the same scalar field with respect now to the second input variable, x2. So now I go term by term. The first input variable is x1. So in my first term here, I just have x1 squared, but I'm viewing x1 as a constant now. And the derivative of x1 squared with respect to x2 is equal to 0. Then I move to my second term here, that's x2 squared. The derivative of x2 squared with respect to x2 is 2 times x2. So I'm going term by term, and I'm taking derivatives with respect to the two different variables to produce these two separate partial derivatives. Let's look at a slightly more complicated example. This is the scalar field g on 3 variables, and the formula is g of xyz equals x times sine of xyz. So now I can take 3 different partial derivatives because I have 3 different input variables. So what happens if I take the partial derivative of g with respect to the first input variable x? So the notation I could use here is curly g over curly x, but instead I'm going to write this as g sub x. So now I'm going to take my expression and view y and z as constants and take a derivative with respect to x. So in order to do this, I'm going to need the product rule here. So the product rule says keep the first term and then differentiate the second term. So this is going to be x multiplied by the derivative of sine of xyz with respect to x. So that will be cosine of the inside. So that's cosine of xyz. But then the chain rule says I have to multiply by the derivative of the inside with respect to x, which will be y times z here. So my first term is xyz times cosine xyz. But then to complete the product rule, I then hold the second part constant and multiply by the derivative of the first part. Well, the first part's just x, so the derivative is 1, and then I'm just multiplying by sine of xyz. So I've used the product rule to calculate this first partial derivative. Now let's take the second partial derivative. The second partial derivative will be with respect to y. I won't need the product rule this time because I'm not multiplying expressions involving y together. This is just a constant x times sine of the constant x times the variable y times the constant z. So now I'm taking cosine of the inside multiplied by x multiplied by the derivative of the inside with respect to y. That leaves me with x times cosine of xyz times the derivative of the inside with respect to y, which is x times z. So when all is said and done, we end up with x squared times z times cosine of xyz. For the partial derivative of g with respect to the third input variable, again, I don't need the product rule because I'm not multiplying expressions involving z together. Here, I'm just taking x times cosine of xyz times the derivative of the inside with respect to z, which is x times y. So I end up with x squared y times cosine of xyz. Let's do a third example. This is another scalar field on R3 called h, and the input variables here are r, s, and t. And the formula for this scalar field is r times e to the r squared t. So again, because I have 3 input variables, I can take 3 partial derivatives. If I take my partial derivative of h with respect to r, here I'm using subscript notation, I'll need the product rule. So this is r times e to the something involving r. So if I apply the product rule, I'll keep r and then take a derivative of e to the r squared t with respect to r. So I'm viewing s and t as constant here. Well, the derivative of e to the r squared times t will be e to the r squared times t multiplied by 2rt. And then when I multiply by that by r, I end up with 2r squared t times e to the r squared t. But I'm using the product rule here, so then I have to add the term where I keep the second and then take a derivative of the first. The derivative of r is just 1, so I'm just left with e to the r squared t. So I needed the product rule to calculate this first partial derivative. Now for my second partial derivative, this will be with respect to the variable s. And if we notice here, there's no s's in my expression for this particular scalar field. So even though this is a somewhat complex expression, since there are no s's, the derivative of all this with respect to s is just 0. So my partial derivative of this scalar field with respect to the second input variable s is equal to 0 here. So Even though one of the input variables is s here, the formula has no dependence on that second input variable, so the second partial derivative is 0. For my third partial derivative, this will be with respect to the variable t. Here, I just need the chain rule because I'm viewing r as constant. So I end up with r times the derivative of e to the r squared t with respect to t, which is e to the r squared t times r squared. So when that's all said and done, I end up with r cubed times e to the r squared times t. So these are 3 examples of taking partial derivatives of 3 different scalar fields. Let's do a few more just to see more examples. So in this next example, I have a scalar field f on 3 input variables, and the formula is f of xyz equals y times z times the natural log of 1 plus x squared. So if I take my first partial derivative, this will be the partial derivative of f with respect to x. Again, I'm using subscript notation. So the part where x appears is inside of the natural log. So y and z are constant, so they'll remain. Then when I take the derivative of natural log of the inside here, I get 1 divided by the inside, which is 1 plus x squared. And then I finish using the chain rule, which demands that I multiply by the derivative of the inside, 1 plus x squared, with respect to x. So that'll leave me with this 2x in the numerator here. Then when I take a derivative with respect to y, the other 2 variables, z and x, are constant. And this is just yz times natural log of 1 plus x squared. The only place where y appears is in the first term, and it's just y. So the derivative with respect to y is just equal to 1 times the rest. So partial derivative with respect to y is z times natural log of 1 plus x squared. Same goes for z. I have z multiplied by y times natural log of 1 plus x squared. When I take a derivative with respect to z, that z just becomes a 1, and then I'm left with everything else. So partial derivative of f with respect to z is equal to y times log of 1 plus x squared. And here's another example. This is a scalar field on 2 variables. This is g of xy equals quantity 1 plus x squared raised to the 1 plus y squared. So here it looks like I have variables in the base and variables in the exponent. So what happens if I take the partial derivative with respect to x? Well, x only appears in the base here, and even though there is a variable y in the exponent, I'm thinking of that as a constant. So how do I take the derivative here? I'm going to apply the chain rule, which will require me first to apply the power rule. So I'm going to drop the exponent 1 plus y squared. Remember, that's a constant with respect to x. So I get 1 plus y squared, multiplied by my base, which is 1 plus x squared, raised to the power minus 1, which is just y squared. And then I need to multiply by the derivative of the inside here. That's what the chain rule demands that I do. Well, the derivative of 1 plus x squared with respect to x is just 2x. So that's a nice exercise. This requires us to understand the power rule and the chain rule, and it requires that we understand that to take the partial derivative with respect to x means we view the base as having the variable in it and the exponent as being constant. However, that's flipped when we go to take the partial with respect to y. Now, the variable is in my exponent and the base is constant. So this requires that we use exponential rule. Exponential rule says the derivative when the variable is in the exponent says we keep the expression, so that's 1 plus x squared raised to the 1 plus y squared. Then we multiply by the natural log of the exponent, which is natural log of then we multiply by the natural log of the base, which is the natural log of 1 plus x squared. But now to finish, we have to apply the chain rule, which says we multiply by the derivative of the exponent. And the derivative of 1 plus y squared is equal to 2y. So again, another nice exercise forcing us to confront the chain rule with the exponential rule, and then also recognizing that we're viewing the base as constant here and the exponent as variable. Okay, so that's a bunch of partial derivatives of a bunch of scalar fields. So I'd like to finish here by offering an interpretation. So remember this example we started with. If temperature in R2 is measured by this scalar field, y cubed minus x squared minus 2xy degrees Celsius, well, I can use that scalar field to directly measure temperature. So at the location 3, 1, temperature here is equal to 4 degrees Celsius. So I'm plugging in x equals 3 and y equals 1 in this expression to get a direct measurement of temperature at a specific location. But let's say now that we take our partial derivatives of this scalar field. So with respect to x, the partial derivative should be, let's go term by term. This will be 0 plus 2x minus 2y degrees Celsius per meter, if I'm measuring distance in meters here. And then with respect to y, term by term, this is 3y squared plus 0 minus 2x. And again, the units here would be degrees Celsius per meter. So those are my two partial derivatives. And what good are those two partial derivatives in this example? Well, if I'm interested in information at this point 3, 1, let's say that I plugged in the numbers 3, 1 into my partial derivative with respect to x. The idea is that in the x direction, if I traveled from 3, 1, I would be experiencing an increase of rate of temperature by 4 degrees Celsius per meter. So if I plug in x equals 3 and y equals 1, the output for the partial derivative with respect to x is equal to 4 degrees Celsius per meter. If instead I plug in the point 3, 1 into the partial derivative with respect to y, the output here ends up being negative 3 degrees Celsius per meter, which means that if temperature is 4 degrees Celsius at the point 3, 1, if I travel due north, I would expect a rate of decrease of temperature to be 3 degrees Celsius per meter. So what this is saying in the figure is that temperature at the location 3, 1 is 4 degrees Celsius, but due east, temperature is increasing, and due north, temperature is decreasing. I had a positive partial derivative with respect to x at the location 3, 1, and I have a negative partial derivative with respect to y at the location 3, 1. That's what's telling me that temperature is increasing in the eastward direction and decreasing in the northward direction at the location 3, 1.